Okay, excellent. So, first of all, hi everyone. Welcome. Welcome to my talk about what I call the function dissection lab, where we're going to be taking apart some Python functions to see how they work. We could do this for hours. Maybe more specifically, I could do this for hours. So this is going to be an intro dissection lab. It's sort of like, I don't know if you had to do this in middle school or high school. You do like a simple dissection of an animal to sort of understand how it works. But like, obviously, when you're older and more competent, you can do it in even greater detail and take longer on it. So we're going to do light stuff, simple stuff today. I am going to use, as you see here, hopefully on your screen, my Jupyter notebook on my web browser on my computer. I actually have this going to a mirror on GitHub. So if you go to my GitHub account, github.com/Reuven, you'll see there's a repository there under Science Circle Functions. And I'm going to actually copy this URL into the chat. And right now it doesn't have anything in it, or barely has anything in it. If I can find the chat. Here we go. I'll send this to everyone. And this will be around after the talk as well. So if and when you want to take a look at this after I'm done talking and walk through it and look through it, you're totally welcome to do that. This will be updated about every 2 minutes automatically while I'm giving my talk. So what are we going to talk about? What are we going to deal with? So first of all, we're going to talk a little bit about what happens when we define a function. And we're going to talk a little bit about bytecodes and Python compilation. And then we're going to talk about some attributes of the code object. And you're going to see, or I should say, maybe the code attribute of a function object. And we can, as I said, get really, really deep into the weeds here. I should add, I love it when people ask questions. I really, really love it. So I'm going to stop every little while, check to see if there are any questions. You can, I guess, put them in the chat or in the Q&A. I'm not sure exactly what people have been doing. Everything is fine with me. I'll take a look, see what people have to say, and then I'll go on to the next thing. And as you can see, these topics are very open-ended. So I've got about an hour to talk. Believe me, I can fill that and more with this stuff. So I'll sort of roll with how things are. I should add, if things are not obvious to you, if I'm saying things that are confusing to you, don't be shy. Please do say so. Please tell me. And that way we can definitely make this session as good as possible for everyone involved. So let's start off with this. Let's say I say here, def hello name, return hello name. So what have I done here? And you might say, oh, I defined a function. But let's be more specific. What I did was actually two different things. First of all, I created a function object. We'll talk more about that. We're going to talk a lot about that. And the second thing is then I assigned that function object to a variable. In this case, hello. But what does this mean, I created a function object? So we have to remember that in Python, everything is an object. And that means everything follows the same rules, right? People love to talk about object-oriented programming as something very sort of mystical or magical, or it's like, really, it's become almost like a religion for some people. But in truth, object-oriented programming is a way for us to organize our code. It's really a logistical and organizational methodology so we can keep track of it, write it more easily, maintain it more easily, debug it more easily. And so by everything being an object, we know that the rules for everything are going to be the same. It's going to be consistent. It's going to be easier for us to understand. And so functions follow these same rules as well. This means that while we often think of functions as verbs, which do things, they are also nouns, which we can store in variables, pass to other functions as arguments, and everything else you can do with strings, lists, tuples, sticks, and so forth. Okay, and this distinction here between creating the function object and assigning it to a variable, that's critical. Because basically, when we create a function object, when we define our function, Python actually takes a look at our function and writes all sorts of hints to itself about what's going on there. So when we define our function, Python's compiler looks at the contents of the function, or like the function's definition, and writes all sorts of hints to itself for how to execute things down the line. That's very nice. But wait a second. Wait a second. What do you mean Python's compiler? Many people who work with Python, even if they've worked in it for years, are unaware of the fact that Python is actually a compiled language. And so Python is compiled in the same way that Java and .NET are compiled. So basically, first, the code is turned into a universal assembly language. In this case, they're known as bytecodes, right? And this is done in Java. When you hear about the Java bytecodes, right? The Java virtual machine is executing that sort of stuff. That's what's happening in Java. The same thing also happens with, what was I going to say, with .NET, where it's turned into bytecodes there. So it is compiled. It turns out that Python's compiler is kind of dumb compared with the Java compiler, compared with the .NET compiler. That is actually going to be changing in the coming years, it would seem. But overall, yes, compiled. And then those bytecodes, right? And this happens once when the function is defined. And then those bytecodes are executed by a Python interpreter every time we run the function. Again, this is exactly what happened in Java and .NET. That's why you need to update your Java system in order to get certain functionality, why you need to update .NET in order to get certain functionality, and why you need to update Python in order to get new functionality, even if someone else wrote that Python program. So they wrote it on their computer, they give it to you, but it's not compiled yet. You need to run it on your computer, and when you run it, you're actually compiling it. We don't separate, we in the Python world, it's extremely rare to separate the compilation and runtime steps, right? Normally, when you run, put in quotes, a Python program, it's first compiled and then executed. So really, like, it's super rare for us to compile things into bytecodes, although it happens with modules all the time. Okay, so what does this mean? What do we care about? Like what's going on here? So let's take a look at our function. Our function here, our function hello, was compiled. Let's take a look at the function object. So if I say here, hello, what's the type of hello? Remember, hello is a variable referring to a function. And if I say, what is the type of hello? Oh, it's a function. That's great. Just as the type of an integer would be int, a type of a string would be str, type of a dictionary would be dict, and so on and so forth. So it is an object in the Python world. And in theory, you could even create a function with this function type. We're not going to do that here. That's like kind of weird, wacky stuff. Okay, but since hello refers to a function object, and since all objects in Python have attributes, it stands to reason that our function object has attributes, and it does, including the dunder code attribute, which contains, the byte compiled, core of the function object. So if I now say hello.dunder code, by the way, here I'm calling it dunder code, which means double underscore before and after code, right? That's like Python slang, you might say. And so what we see here is that indeed we have a code object, right? Code object hello at, and this is just the location in memory. We can't do anything with it. Here's the file it came from. Well, it came from a file inside of Jupyter, so we don't care. Line 1. Okay, that's not interesting. What's much more interesting is that this code object also has attributes, because it's an object, and everything in Python is an object. Everything in Python, every object in Python has attributes. So I can say here, for example, what's the dir of hello.dunder code, right? What attributes does this object have? And we're going to see a bunch of boring ones, but then we're going to see a bunch of really interesting ones that all start with the letter CO or CO underscore. These are the hints that Python has defined for itself in order to keep track of things. And the first and most important one is CO underscore code. So hello.undercode, CO code. Let's look at the bytecodes themselves. And I don't know about you, but for me, this is really hard to read and understand. Why would that possibly be the case? It's just a bunch of hex codes, right? Yeah, well, I don't know what these hex codes are. You gotta be kidding me. Moreover, we can see it's a byte string. It starts with the letter B before the opening quote. And that means that we have a byte string here, meaning it's not characters, it's bytes. It's individual numbers, actually. If we had some ASCII characters in there, and I guess we do, like the pipe here, and there are probably some others, then, yeah, well, I guess the S here, then those would be represented as, well, printable characters. Everything else is just listed as hex codes. So, excuse me, it's been a long day. So how can we see, or how can we turn the bytecodes into something readable and understand what Python is doing? Well, we can use the dis.dis function, which comes in Python's standard library. So I can say import dis, and then dis.dis of hello, and watch what's going to happen. This is what Python is actually executing when we call a function, when we call this function. So let's go through it little by little. And let me also explain to you what's going on here. So we have here, this is the line number in the code that we defined it. Well, wait a second. Let's take a look. Where did I define up here? Let's go up, 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 up. Here we go. Okay, so I guess, oh, here we go. Return. Right? So return is on line 2. And sure enough, it says here we start on line 2. And what is on line 2? Well, the first thing we're going to do is load a constant. And by the way, these numbers here, 0, 2, 4, 6, 8, 10, these are the byte indexes. So each bytecode is a command. You can think of it as like a made-up assembly language. And so first we have a verb, and then we have a noun. So the verbs are on the even bytes, 0, 2, 4, 6, and the nouns, the objects, as it were, right? Object in terms of subject, object, subject, verb, object, are on, or the nouns are in the odd bytes. So here we're loading the constant 1. Stop for a moment. Constants. I didn't think Python has constants. Does Python have constants? The answer is no. Do Python functions have constants? The answer is yes. They are stored on the function object based on the compiler's reading of our function body. And so what are these things? These are all of the literal values, integers, strings, etc., that can be stored once and then used multiple times. And even if we're not going to use them, the compiler does this. So what do I mean by this? So basically, if I say here, hello.undercode of CO consts, right? Let's see the constants. And the constants are in a tuple. And we see 3 constants. We see none, which is always there, and I think always at index 0. We see hello, space, and we see exclamation point. So basically, our function had an F string, that said hello, the variable name, and then an exclamation point. And we wanted to return that string. So how is Python doing it? Well, it's going to first load the constant hello. Then it's going to load the variable name. Then it's going to format that value. So it's going to find out, how do I take this name? How do I take this string and format it appropriately? Then we're going to load the constant exclamation point. We now have 1, 2, 3 things that we want to join together into a new string. What do you know? We're going to say build string 3. And we get then a value, a new string. And what are we going to do with that value? We're going to return it. Those of you who have studied computer science might have heard of stack machines. And this is a classic stack machine. where I'm going to load this constant, I'm going to get the value, I'm going to get this constant. I now have 3 values. I'm going to run build string on those 3 values. They're going to be popped off of the stack, and then the value that replaces all of them is going to be returned. So this is what happens when we call our simple function. And we can see a few things here that might surprise you. First of all, this whole constants business. Then you can see here, load const 1. What is this 1? It's the index inside of the constants tuple. So load fast. What does fast mean? Fast means a variable, local variable, meaning get the value from the local variable name. And name, of course, where do we get the value for name from? Well, whoever called the function passed an argument, and that argument was assigned to the parameter name. And parameters are, by definition, local variables. And then we load another constant. Now, I must say, when I started using f-strings a number of years ago, I guess it was a long time ago already, they've been around for a while, since Python 3.6 or so. When I started using f-strings, I thought that it would basically say, okay, here is the dynamic part inside of a regular string. But no. It breaks the string apart. And it said the f-string apart. And it says, yeah, there's the dynamic stuff, but before that stack, after that stack, we'll get them together. So it's a different way of doing things that I would have expected. By the way, this none, it's there because it has to be there, but we're never going to use it. It's not going to happen. Oh, we don't use it here. That's how, by the way, if you have a function that does not return anything, that's how it always is able to return none, because none is always there. All right, let me stop there for a moment and see if there are any questions in the chat or elsewhere. Anyone want to ask about what's going on here? Questions, comments? Stunned silence. I'll give you another few moments to ask questions if you have any, and then I'll move on and show you some other cool things that we can see with these bytecodes. Okay, excellent. So what's next? Well, we see these bytecodes, and that's nice. But remember how I said we're passing a value to our name parameter? So if I say hello world, right? So what's happening? Well, we have parameters, name, and we have arguments, world. And so Python assigns world to name. And this is a positional argument assigned based on position. And sure enough, it works great. Right? So this is always how Python is going to try, unless we do some fancy footwork in other ways. So we have the argument here, world. We have the parameter here, parameter. There we go. Sorry, it's just like annoys me. All right, now we've got that working. So what happens if I call hello with 0 arguments? Well, I say hello, and we get an error. And what kind of error? It says hello is missing one required positional argument called name. And my question is, how did Python know that we needed to pass one positional argument? How did Python know that the parameter to which it will be assigned is called name? Right, these are things that we kind of take for granted when we're calling functions, but clearly there's got to be some sort of rule there, right? It's not just hocus pocus. And so basically we can look, let's look in our function object to find out. So I'm going to say here, hello.dundercode.co arg count. And this is how many arguments does the function expect? What do you know? 1. And let's look, let's find out. Well, let's just do then hello.dundercode co var names. And what are the names of the local variables? And this is a tuple of strings. And we see that there's only one. So since there's only one local variable, and since arg count is 1, that local variable is a parameter. It must get a value from the caller. That's how Python knew that we needed to provide a single argument. That's how Python knew that it needs to be assigned to name. Okay, so basically when we call our function, Python does a quick check. And when were these things set? When was arg count set? What was var name set? They were both set at compile time, when our function was defined, when our function was compiled. Okay, what happens if I call the function with too many arguments? Well, same thing's going to happen, right? If I say hello out there, it's going to say, wait. Hello takes one positional argument, but two were given. Right? So this actually, this makes sense. We're starting to see how this makes sense, that Python knows how many we need. Well, wait a second. How about when we have a default argument for a parameter? And you might have seen this before. I can say, for example, def hello, name equals, let's say, no name. Return hello name. And so now what's happening? Well, we've done the same thing as before. It's basically the same function as before. By the way, let me just add here. People sometimes believe that in Python, we should be able to define a function once with 0 arguments, once with 1 argument, once for 2 arguments. That is impossible. I know many languages provide that sort of functionality where we can have different function signatures for the same function, and you define it once for 0 arguments, one for 1 argument, one for 2 arguments, once for strings, once for lists, once for tuple, all these different things. You can definitely do that in other languages, not in Python. In Python, you define a function, that function is assigned to the variable. You define the function a second time, the new function is assigned to the variable, and the old one, poof, bye-bye, it's gone. You cannot have more than one version of a function at a time assigned to the same name. Although it's a little bit of a lie because there is a way to do that, but it's through a lot of magic, fancy footwork, and we're not going to talk about that here. So here, so now, name has a default value. Well, wait a second, excuse me. Wait a second. How does Python know into this default? And where is the default stored? So let's answer the second question first. If I say hello.under defaults, this is a tuple of string or tuple of values taken from, with default values. And so sure enough, hello.under defaults, since we defined it here, is a tuple with one element, the string no name. And so if I call hello with one argument, so if I say here, hello world, what's going to happen? Well, we have parameters, name, arguments, world, and world is assigned to name. And we're great. What if I say hello with nothing? Then the parameters, name still needs to get a value. The arguments, nothing so far. Aha, so Python says, wait a second, I need one value. I know, right, then there's only one parameter here. So I'm going to go to under defaults and I'm going to grab the last element. And so arguments is going to get no name taken from under defaults. And sure enough, that works just fine. Okay, so this is how we can define a function with defaults, and this is how it works. Python checks at compile time. Python looks for the argument. If the argument is there, then the default is ignored. If the argument is not there, then Python has to go to under defaults and retrieve it from there. Can I have a function with more than one default? The answer is yes. But default values, or I should say parameters with defaults, must come after parameters without defaults. Meaning, mandatory parameters before optional parameters. Okay, I'm going to show you an example or two, and then if people have questions, feel free. It's really, really okay to submit questions, unless all is good, in which case, hey, fantastic. So what if I do this? What if I say here def add first and second, return first plus second, right? That's going to work. Add of 10 and 3, that's good. But now let's add some defaults. So if I say here def add first equals 3 and second equals 8, return first plus second. So now I have my function there, and now I can say add of, right? And I can say add of nothing. So first is assigned, let's say here, parameters, first and second arguments. So since I pass nothing, first will get 3 and second will get 8. But both values are taken from Dunder defaults. And let's take a look at Dunder defaults. Add of Dunder defaults. It's going to show us 3 and 8. So basically, we pass nothing. Python says, wait, you need 2. So we're going to take the first one, assign to first, take the second one, assign to second. All is good. Right? What if I pass a value for first, but not second? So now I can say add of, let's say, 4. So sure enough, and this is totally fine, because what's going to happen, we're going to say parameters, we're going to say first and second, and arguments, we're going to first is going to be 4, second, oh, we didn't get one, but that's okay. We go to Dunder defaults, we grab the second value from there, we put in an 8, and we should have 12, and sure enough, that's what we get. So what if I pass a value for second, but not first? What if I say here, add of, let's say, well, how am I even going to do that? Well, I could actually do it with second equals, something else. I could say second equals, 9, right? Using keyword arguments in name equals value form will work. Otherwise, though, you must, right? The first, always, I should say, always. So put it here, and always. When defining a function, let's say mandatory parameters without defaults must come before optional parameters with defaults. And then when calling a function, basically, if we use positional arguments, then let's just say this: calling a function, positional arguments need to come before keyword arguments, i.e. those in the form of name equals value, like I did above. We haven't really talked about keyword arguments, so if that's confusing to you, ignore it, forget it, don't worry about it too much. Okay, any questions or thoughts until here? Okay. So what we're now seeing is that there's this very, very standardized mechanism. When I define a function, right, Python writes it down, it uses the bytecodes, it figures out what are the parameters, how many arguments does it need to get, what's it going to execute, and then every time we have to call the function, Python does the assignment, and then it calls the function. Notice also that when we actually do call, when the function body executes, it has no way of knowing how those arguments got there. It just knows that they're assigned. Those are local variables, those are done, and that works just fine. So let me ask you something about this, like, dangers with defaults. So what if I do this? What if I say here def add 1 x? I'm going to say here x append 1. And now I'm going to say my list equals 10, 20, 30. So we define a list. And now if I call, let's even do a return x. And now I call add 1 to my list. So what's it going to return? Well, it's going to return, it should return 10, 20, 31. Why? Because I'm calling with my list. X then, the local X, is going to be the same as the global add 1. Those two variables the global my list. Local X and global my list refer to the same list. Add 1, we'll append to it. And then we return X, we return the local variable, but that's just referring to the global one, and it returns. And so sure enough, when I say add 1 to my list, I get back the list 10, 20, 31. And if I look now at my list, it was changed. by the function type. And if I do it again, I'll add another one. So if I say here, add one to my list, I look at my list, sure enough, we added 2 ones. Okay. Oh, wait, there's something in the chat. Fantastic. Nishant is asking, is there any specific reason why Python does not allow function overloading like in C++ and other languages? So the reason is the way the function is, I'm sorry, that the language is constructed. In Python, a function is a first-class object. Functions are not in their own namespace. So the same namespace that contains values like integers and strings and dictionaries also contains functions. And so just as you can't say, so here, let me give you an example. If I say x equals 7, and x equals 5, and I say print x, it's going to print 5, right? Because, of course, it'll print 5. That's the most recent value assigned to x. In the same way, when you define a function a second time, you are assigning the new version to the variable. So in order to have function overloading, you need to have a special separate namespace for functions than for data. And then it needs to be treated specially when you invoke it. And the Python people said, we don't want to do that. We don't make everything super, super consistent. And then what we do is we have functionality, we have sort of flexibility in our parameters and our arguments rather than the function overloading and the multiple dispatch. Okay, hopefully that explains it well enough. If not, do let me know. Okay. So let me just go back here to add one and do one more thing here. Oh, okay, excellent. So what if I'm going to now change it? Let's change add one a bit. Something. All right. So I'm now going to say def add one x equals an empty list. Now we have a default value for x, empty list. I say x append 1, return x. And now I'm not going to call it with a value at all. I'm going to say add 1. What is going to be returned when I call add 1 now? Well, let's think about it. I call the function. X is a parameter. We did not pass it a value. It needs to have a value. So Python goes to dunder defaults and retrieves our empty list. And sure enough, we get back 1. So far, so good. Now I call add 1 a second time. What will be returned the second time? And the answer is 1, 1. And this is where people freak out. And rightly so. Because what the heck is going on here? Well, let's take it step by step. I'm going to redefine the function. So if I now say add 1 dot dunder defaults, right? What default value is there? And sure enough, it's an empty list. Now we might believe that when we define this function, we are saying, when I call this function and I don't provide an argument, I want an empty list. And I want that empty list to be assigned to x. That's lovely that we think that, but that's not what actually is happening. Rather, what's happening is when we call add 1 without any arguments, Python says, aha, there's no argument. I'm going to pull up dunder defaults. And this list, the list that we created at compile time, right? So defaults, and the dunder defaults, the values I could say, in the dunder defaults tuple are defined at compile time, not at runtime. Which means that if we have a mutable value, such as a list in dunder defaults, and then we modify it inside of our function body, what's going to happen? That modified value will then be used as a default on the next run. This is very bad right? Sometimes people are like, oh, what a cool feature. No, no, no. This is not a cool feature. This is a bad thing. And so basically, the solution is never, ever, ever use mutable defaults. I should add, most IDEs and code checkers will point to this and tell you not to. And the problem is that, like, it's very possible to have code that works just fine using mutable defaults until one day it stops working fine and you are super thoroughly confused, which is not good. All right, so don't use mutable defaults, which raises the question of, so how should I rewrite add one to do the right thing without mutable defaults? And there's no perfect answer for this. My preferred answer is to define the default to be none, which is, of course, immutable. So I can say here, that's none. So X is none, thus immutable. And then I can say at runtime, I can, potentially reassign X. So I can say here, for example, if X is none, then X is an empty list. And so now this list is created at runtime, and thus is new with each invocation. And so now if I say add one with nothing, we get one. Add one with nothing, we get one again. And one again. So we don't need to worry about it anymore. All right, so this whole mutable defaults thing, be very, very, very careful of it. And again, most modern IDEs will say something about it if and when you need. Okay. Questions, comments about any of this so far? Okay. So we've seen quite a few little pieces here of our function object, what's going on there. I want to show you one more thing or one more issue that has to do with them, and that's the topic of scoping. Oops. So basically, Python has very consistent, clear scoping rules. And scoping, in case you're not familiar with it, refers to when variables are available, defined, and also when they disappear. Now, if you talk about local versus global variables, this is, that's scoping. All right, so let's start off with, for starters, if I say X equals 100, and I say for I in range 5, X equals I to the second power, right? What will X's value be here? And let's see, it's going to be, this is basically a question of, is this a local variable? Does this variable X, right? Is this X the same as the X I defined on line 3? Or is it local to the loop? And in many, many languages, X here would be local to the loop, but not in Python. In Python, a new block with indentation does not open a new scope. It does not keep things shielded from the outside. It's in exactly the same scope as before. So scoping rules in Python. So there are only 4 scopes in Python. They are known as local, global, built-in, local, enclosing. Global and built-in, but we're not going to talk about enclosing here today. All right, and these are often referred to as the LEGB rule. And so the LEGB rule allows us to reason about the scope and understand it. And this is how Python does it as well. So basically, local, we start searching here if we're inside of a function body. And then global, we start searching here if we're not inside of a function body. And then basically, Python starts at either L or G and keeps searching down the list in order until it either finds the variable it's looking for at that level, or it gets to the end and raises a name error. Okay, so let's put this into practice. If I say x equals 100, and then I say print x equals x, what will happen when I call this code? So I run it, and it says x equals 100. And I hope you are not surprised by this. But let's think about how this is working. Are we in a function body? No, we're not. We're not in a function body. So Python starts searching at the global level and it asks, is x global? Well, how can we find out? We can check by looking for the key x in globals. That's right. There is a function called globals that when we call it returns a dictionary of all the global variables. So if I say x in globals, it'll say true. There is a global variable x. And I can even say globals of x. I'll retrieve the global. And it gives me 100 there. Okay. By the way, never ever use globals in real code. It's really fun to play with. It's really useful when teaching. It's very bad for people to actually use it in day-to-day code. So let's make our code a little more complex now. Spice it up a little bit. I'm going to now say def myfunc print in myfunc x equals x. Then I can say here print before x is x after and myfunc. So you can see that we're going to set x to be 100, and then we're going to define myfunc, and then we're going to actually run things. We're going to print before what's the value of x. We're going to call myfunc, which is going to print the value of x, and then we're going to print after. And the answer is x equals 100 each time. And this is surprising to people who come from languages in which we can't access that kind of variable, that kind of global variable from within a function, at least not easily. But in Python, as you see, thanks to the LEGB rule, it works just fine. So we start off by saying, is x global? The answer is yes, because we're outside of a function body. But then we call our function myfunc, and we get there, and then it asks, well, is x global? It starts, is x local? It starts with LEGB because, well, we're inside of a function body. The answer is no. Wait. How does Python know? How does Python know if x is local? It can check on the dundercode.co var names tuple. So we can say, is x in, I can do myfunc code CO var names. And false, it's not there. So it's not a local variable. Next, we're going to ignore enclosing. Then we say, is x global? The answer is yes. So we get back the value of 100. And then we return here. And once again, is x global? Yes. So you can see that this is how we ignore local variables outside of a function, but we look at them first. We give them first priority inside of a function. Okay. Let's make it more complex now. What if I do this? What if let's get rid of the comments. Now I say here, x equals 200. Now, what will be printed? Well, let's run first. And you'll see here 100, 200, 100. This is the global variable x. And this here is the local variable x. No relation to global x whatsoever. None whatsoever. So when I get to line 9, print the value of x, we're outside of a function body. So we asked, is x global? The answer is yes, 100, done. Then we get to my func. And we say, is x local? And the answer is yes. Really? The answer is yes. Well, let's check. Is x local to my func? We can say my func dot code dot co var names. And sure enough, at compile time, Python wrote down that x was local. And so when we finally run the function, that indication is right there. So it's local, yes, and the value is 200. But then, the function returns. All those local variables defining the function disappear to go to meet their maker. And now we're back once again at the global scope. We're outside of a function body. So afterwards, is x global? The answer is yes, 100. Okay, questions until here. Any thoughts or questions? Okay. Well, this raises all sorts of problems, right? Like, what if I want to change a global variable? By the way, it's a terrible idea. Usually you should not do it. And this is just if we want to assign to a global variable. Not because we want to change an attribute on a global. But basically, what happens if I do this? And I'm going to swap these two lines here. So this line, right, swap these two lines from before. What will be the answer now? And now it's kind of hard. Now it's kind of hard because, well, when we call our phone, we know that here it's going to say, x is global, or, is x global? Yes, that's 100. But then we get here to a function, and we're right away asking Python to print the value of x. Well, it goes through its usual thing. It says, right, is x local? And the answer is yes, it is local. How? Assigning to a variable inside of a function makes it local. So Python's compiler looks through our code. It says, oh, I see. You're assigned 200x. That makes x a local variable. End of story. I don't care how many other x's there are. I don't know how many x's you have. Okay. So what's going to happen when I run this? I'm going to get an error, an unbound local error, which is a fancy way of saying, dummy, you have to give x a value before you can retrieve from it. Now, this is a really, really unusual Python error, because normally in Python, you cannot have a variable without a value. Either your variable doesn't exist, or it does exist and it has a value. But this notion of the variable existing without a value is like super weird. But it's because Python writes down all the local variables at compile time, and at runtime, we don't necessarily have a value. So if you ever see unbound local error, it's because you are you're retrieving before you assign inside of a function. Now, there is another way to go about this. But let me first say, I'm going to say dis.dis of my func. What are the bytecodes for my func? And we see here, we're going to load the global function print. We're going to load the constant in my func, fast x, form a value, build string with these two things, call the function print, and pop it. So we print all the things here. And then we load the constant 200. We store it into the local variable x. Right? So we're asking for the local variable x load fast, and then we're storing into it. This is how the bytecodes see it, what we're trying to do. Okay, well, let's do something a little different then. I'm going to Okay, I'm gonna paste this here. What if I do this? I'm going to keep exactly the same code, but what I'm going to actually do is I'm going to say here, global. Well, first of all, don't do this, right? But what if I go back here and I now say global X? This means, this tells Python's compiler not to tag X as local, but rather as global. And now, when I assign to X, we're not assigned to a local X, we're assigned to the global variable X. So now we have X is 100 on the first pass, X is 200 inside of my func, but when we return, we see that the global X has also changed. It has also been modified. And so and by the way, what if I now say dis.dis of my func? Watch what's happened. We no longer have local variables. We load a constant, fine. We store it to the global X, And then we load globals, global X. So really, this global statement is sort of a hint to the Python compiler what we want to do and how we want to do it. Okay, questions or comments until here, and then I'm going to do a little bit more, and then we're going to finish up, and we'll have some time for Q&A as well, or additional Q&A, I should say. I'll give you another few seconds, and if not, then we will continue. Oh, great. Chat. What if we do the following? See, I'm just going to copy this here. So Karen is asking, what if we say def my func X is 200, print X, and then X is 100? So, okay, so let's take this one step at a time. When I define my func, this X, so this X is only local, only exists when we call my func and inside of the function body, right? So basically, I define my function, but when I define the function, X will never be assigned 200. It only assigns it a value when we actually run the function. And then I can say print X. This X, if I get rid of my, this will print a global value X if it has been defined. If not, error. All right, and now finally, here we define X as a global variable. The value 100. It looks to me like it's sort of like backwards from what we would want to do, per se. I'm not sure if I answered your question well, but now we're going to see X equals, it's going to print 200. Why 200? Because previously, before I did anything here, X was 200. And so this here doesn't actually assign anything, and this here does assign, but it's too late. We've already printed. And hopefully that was helpful. So I'm just going to show you one more function. If I say dis show code of hello, or great. So if I say show code of hello, this is the function we did before, right? Did we do? Yeah. So we see it's not going to show us, show code doesn't show us bytecodes. It shows us all of the hints that Python wrote down for our function. So it tells us where it was defined. It tells us how many arguments, how many positional only arguments, a special kind we're not going to have time to talk about today, how many keyword arguments, other special kind we're going to talk about today, number of local variables, the stack size, how much size does it need in memory in order to work with our, our values. The flags here are basically, well, they are bit fields to double check sort of the special stuff having to do with their function, we have the constants, we have the variable names. So show code is a great way to sort of summarize your function and what it does. All right, so I think I'm going to stop here. If there are any more questions, I'm very, very happy to answer them. I hope you see, though, that the fact that Python functions are objects and are functions gives us this incredible flexibility, both to especially to understand what's going on inside. And we can really pull them apart, look at the contents of these different attributes, and realize that, as I like to say, Python uses Python to implement Python. And so our functions contain ints and floats and strings and lists and tuples and dictionaries, just like our programs do. Okay. Questions, comments, thoughts from anyone? Does Python support out-of-order execution? I'm not sure I know what that means. I think I'm going to guess, but if you could maybe be a little more specific, I would appreciate it, Nishant. Oh, as you were saying, maybe some, all right. So, Jousef, I'll give some best practices to make everyone happy and not like have their brains coming out of their ears. Let's see. Mutable is asking how to check what all function exists in Python. So if you want to know all the different functions, we didn't talk about that last. I'll add one last thing here, which is the final place that Python looks for things is built-ins. And these are very familiar to us. They're print, len, int, stir, list, dict, etc., which are not keywords, and you can get yourself into real trouble with that. You can redefine them. So if I want to know what functions exist in Python, I can say dir of built-in, and I can get a list of, well, it's going to be all the built-ins, but these are the functions that exist here. And if you want to, yes, it'll be mixed up with some classes and mixed up with some exceptions. I can also say dir of globals, or I can just say globals, right? So, what global values are defined. And so if you do these together, you'll get all the functions. You won't get the methods because the methods are attached to particular objects, but you will get the functions. You probably don't want to do that, I should add, but you totally can. All right. Nishant, I did get more specific stuff from you, so I'm going to guess what out-of-order execution means. Like, I'm going to take it at face value. Then the answer is no. That basically Python does the first thing, then the second thing, then the third thing, then the fourth thing. If you wanted to do, I guess, out of order, then you have to return from a function or something. You can use exceptions. There are all sorts of little tricks you can use, but at the end of the day, each bytecode, is executed one by one, unless you have ifs or breaks out of loops or that sort of thing. Excellent, thank you. Jousef was asking me for some best practices at the end to make everyone happy. Let's do a few basic ones here. Oops, hello, what's going on? Oh, there we go. A short, my favorite ones. Let's see. So, optimize for readability, not execution speed. This drives me completely and utterly bananas. That basically people are like, yeah, but how much memory does it use? Yes, but how fast does it run? All right. The number one thing you should be worried about when you write code is what will someone else think when they read your code? How easily can they go into your code and debug it and fix it and maintain it? I don't know how often this has happened to you, but it definitely happened to me where I go into code, I'm like, who was the idiot who wrote this? Oh my God, it was me. And then I realize now I'm really in trouble, right? So write it with good variable names, with good function names. I don't mean write it with comments. Comments are sort of a crutch that you use if you don't have, but try to write it to be clear. Idiomatic Python is usually the best. So why create a class? Let's do it this way, right? Best, fastest, easiest, to, fastest to execute is to read. Right? People are like, oh, I don't know. Why should I be using a tuple here? I could just write a whole new class. If people in Python use a tuple, use a tuple. And so write classes when you need to, not whenever, not for everything. And this also drives me bananas, that especially people who come from the worlds of C++ and Java and C#, they're like, oh, I have a problem. I better write a new class. Maybe you'll write a new class, but you don't have to. You can solve many, many problems with the core data structures. Those are like the first ones that come to mind. I know they're very general. Nishant is also asking, can you suggest some references or books for becoming becoming familiar with low-level details of Python 3. So Anthony Shaw, let's say here, here we go, book about Python internals. I only know one, and it's Anthony Shaw's C Python internals. Right? It's a great book. I've only read maybe about a third of it, but the parts I've read, oh my God, they're so great. Definitely recommend it. I'll also say best practice, folks, use, I'll add another 2 or 3 here. Use the standard library. Right? Don't reinvent the wheel. Oh, thank you. You can read my mind about that. Great too. Thank you. Really, people are always reinventing the wheel. I would say if you don't use the standard library, or PyPI, if your solution isn't there, right? And then just realize you're going to have to keep learning from other people all the time. I constantly tell people this, whether it's on Twitter or on my mailing list or, in my corporate classes. I'm using Python for about 30 years now. Every single day, I'm learning new stuff about Python, often from people asking questions in courses and presentations like this, which is, for me, that's the fun. All right, folks, I think our time is up. Thank you so much for your great questions. I really appreciate it. I would love to hear from you more online. As I said, I'm on Twitter, I'm on YouTube, I've got a mailing list. I'd love to hear more from you folks. And thank you so much, everyone. Have a great rest of the workshop, and I hope to hear from you in the future, as I said.
Thank you so much, Reuven. It was an excellent presentation. Hope to see you in the second part in the future.